Well, thank you, Bruce, for this very, very nice introduction. My English got a lot worse over these years in Paris, so I tried to. So yeah, I don't know exactly what to show today because it's quite different of what's the main research is here. So I'm going to show a little bit of everything, and I just wanted to start with ircam, the research institute, which is part of the Museum of Modern Art in Paris, right in the center. And ircam is actually underground, under the fountain you see on the right. And it's one of the old institutes where they try to merge science and arts and music. It was founded in 1977 by Pierre Boulez. And it's, I think now it's almost 200 people working there. And they are a big research department. I'm really part of it. And there are also artistic production, concert, and a department for education. So the idea is really to mix both research and music production. So the research, the natural outputs are, it's as in any academic center, papers, industrial outputs, and try to mix that with music where what we do is apply in real concert and dance performances. It's mostly contemporary music. And just to show you, I mean, the R&D department really covers a large span of all the music technology. There are 8 teams, starting with musicology, studying acoustics, studying room acoustic and how to do 3D sound analysis and sound synthesis, computer-aided composition, perception and sound design. And my team, now I started with this team and I became the coordinator of the team 3 years ago. It's called the real-time musical interaction. And just to give you an idea, it's a team of 4 researchers, computer programmers, 1 electronic engineer. We have several non-permanent researchers and on average 4 PhD students plus master students. So it's a group of mainly roughly like 10 to 14 people, just to give you an idea. So I'm going to talk about musical digital instrument. And when I came in the US in last March for a competition of new musical instruments, at the custom, the guy was really surprised when I said that I was working on new musical instruments. They say, everything has been invented yet. It has been invented. What are you doing? Why are you coming here? So the idea is that, okay, we have computer, we have someone, human, and the speaker. And one of the first idea has been developed at ircam for a long time is that actually you have a normal musician, normal meaning playing an acoustic instrument. And then if you record, you can transform the sound in real time and add digital effects. And it's adding electronic music to the acoustic music. So it's a mix between acoustic and electronic music. Now you can, that's really what I started this idea here actually when I was postdoc working with Chris Dovian, who's here. You can also try to capture the motion of the musician. And if you are able to analyze a gesture, mix that to some sound synthesis engine, you can use the motion of the musician to create the electronic sound. And now you can really think, okay, forget about the acoustic instrument. I mean, what about just creating a new object, a new instrument? So just to put things in context, I mean, we all know the violin, the piano, which has been really created a few centuries ago. In the 19th century, the saxophone, which maybe has been a large influence on music, jazz in the 20th century. And if you think about the last century, about the new instrument that has been developed, I don't know if Tony knows when the electric guitar has been patented first. I think the flying hand guitar was invented in 1939. Yeah, I think it's or 31. I think even the first one, the 30s. So it's quite earlier than what people might think. In the 20s, there was this quite amazing instrument that was invented by Theremin that you just play by moving the hand close to an antenna. And it's really one of the first music synthesizer. It has been then used a lot in movies for later, and it has been a little bit forgotten, and it has been somehow rediscovered lately. And it's really went back to all the technology to do sound synthesis, but as you probably all know, I mean, the mainstream is to use a keyboard, which is actually extremely limiting to play sound synthesis, to my view. And in the 70s, there are all the development of the digital sound processing. That's grown a lot, but most of a lot of things are really done to do post-processing, to change the sound with using just a regular computer and a mouse and a keyboard. And now there is interesting things coming in this new century is in the idea of rethinking everything and try to come up with new instruments. So just a few examples of interfaces. You can really think about playing music with, for example, an interactive table, or maybe some of you know you can use an iPhone to play instrument. I think David is an expert in this. So actually now the field of making new digital music instruments, it's really part of a much bigger field that's really changing a lot these last years. It's really the field of human-machine interaction. And you know, all the new gestural interfaces that came up a lot for video games, like the Wii, like iPhone, or the Kinect. And what's really special about maybe my research in this bigger field is that we're really looking at things, we really think about expressivity as we might think in music. It's not just about clicking and selecting something on a computer. It's really be expressive with a computer. So Bruce told me that I need to speak a little bit about optics. So since I'm not doing much in optics these days, I think I should mention the Kinect, which is quite interesting because so for a video game to really measure 3D view and 3D motion, first for a long time they announced that they were going to use time-of-flight technologies, which I thought was interesting. And finally they're using kind of structure light techniques. which you might think it's quite similar to some of the things done here. We can go more in detail about how it works. But they use two cameras, a color camera, a black and white cameras to get the depth. And now it's very cheap, and that's really changing, bringing 3D motion capture capabilities to a lot of people. So going to talk about gesture and sound research. I said it's for music and performing arts in the field of human-computer interaction, and we are really looking at this other field, research field, about signal processing and artificial intelligence and machine learning. And the other things that we're getting it's all the cognitive science about perception, sound perception, motor control, sensory motor learning. I'm going to talk about that. So first, my talk is divided in three parts. First, I'm going to talk about some research I've been doing on just studying musician gesture, because if you want to create a new instrument, you can think, oh, what about just studying existing instrument, like acoustic instrument, and try to understand the musician motion. So there are different ways to do it, and we study a lot the violin, which is very nice because you can really measure very well the motion of the violin using 3D motion capture, like its system mostly developed for biomechanics studies and animation. I'm sure you're all familiar with that. We've also designed some sensor we directly put on the bow to measure, for example, the bow acceleration. And we really try different systems combining video and sensor-based systems. So it's an old video. I mean, when I arrived at IRCAM, trying just to show you, there is acceleration accelerometers attached to the bow, and you see in real time the data. So what's quite amazing is that when you do this measurement, you have a quite complex shape, and you think that most of the curve you get is noise, but then you ask a musician to play twice the same thing, and you have not exactly, but extremely close the same thing. So you think you really need to analyze that with some signal processing to really make sense of it. Just another example is measurement on violin using 3D optical motion capture. Where you can also have the whole body. So look at the pattern. You see this 8 pattern, which is very nice, and it's actually well known from people teaching violin. They know that actually when you do this type of this piece, you end up doing an 8 pattern. But it's quite nice to really see it when you can measure it. So if you measure the whole gesture, the whole motion, you can then feed a violin physical model and do to do sound synthesis. So it's a virtual violin using all the physics, and then you get, for example, this type of results. So what's very interesting is that if you compare with other way of doing sound synthesis, it's not maybe you can have even better sound, but here you keep all the expressivity because you actually measure the motion, and then you can find it in the sound. But here it's the whole, it's a whole section. So one of our thinking was, okay, how can we divide our measurement? How can you make sense of it? So we studied different bowing style. This is what is called détaché. Where is the sound? The sound disappear. Spiccato. And martelé. So it's really different way to different motion type with the bow. And if you do some analysis, you can really cluster them and separate the different motion. So it's like, it's kind of the ideal case where you have a malignant tumor and non-malignant stuff. And after that, we built a real-time system to actually detect these different bowing styles. So here's the normal détaché. So what you see on the axis, it's the acceleration of the attack, and this is the acceleration or deceleration when stopping the bow. So it's really the kind of the ideal case playing scale. It's quite easy to do it. When somebody is really playing an actual piece, it's not as ideal than that. So we try to think about how to characterize this motion and try to think about some biomedical or physical constraint when you actually play. And we found in a quite old paper in the 80s where they already did that, and you can characterize different motion and to think as is the motion correspond to minimizing different effort cost, which means that you can minimize the impulse or if you consider 1 point on the bow, and if you from the physics, you consider what is the curve that's going to minimize this quantity. This is the acceleration. You have this type of curve. And if you want to minimize the derivative of the acceleration, which is called the minimum jerk, in motion control, you have a quite different shape. So it's quite close to minimizing the energy. And that's really well known because it's one of the motion law. When you do when you move freely with the hand, you tend to minimize the derivative of the acceleration, and it's really physiological constraint. And this is absolutely not natural motion. It's really more like a robot-like type of motion. And if you think about what we found is that in the violin, you have these two types of motion, and you have also this kind of quite difficult pattern to get because you really have to train a lot, and that's, to my view, one among many difficulties to learn violin is that you have to achieve this type of profile in the velocity to actually play well. And that's really against most of the physiological constraints. So we were able to really show that with real measurement on violin bow. And what's even more interesting is that if you now, so it's two, what is called détaché, so it's really a long note and then martelé with strong attack. And then it's one type of motion, one type of minimization. That's the other type. And what's happening here is that the last one, the player already anticipates the next type. And the previous one, the next one, there is kind of a persistence of this type. So here there is a total mix of the type of motion, and it's really exactly as what we call gestural co-articulation is exactly what's happening when you speak. A phoneme is not the same depending where it is in the with different neighborhood. So it's actually quite interesting because if you try then to do gesture recognition, that's something that's a big problem, because here you can clearly recognize this type and this type, but once you mix the series, then you're in big trouble because your signal is kind of a mixed signal. But what's interesting in music is that actually because this mix is really part of the expressivity of the musician, that's really where you start not playing as a robot and not playing mechanically, and then when you start to articulate sound. Another thing that we found with this measurement is when you try to accelerate your motion. Here you have this first type of motion, and then when you go fast, you switch to a different type of motion. And that's a change of coordination that's very similar to the change of type of coordination that you found between walking and running. There is no smooth transition between the two. Either you walk or either you run. And you find this same type of thing looking at musicians. So I could go over hours or more detail on that, but we found interesting things about different motion coordination and negotiation of the player between physiological and acoustic constraint. Evidence of gesture co-articulation similar to speech. And also, I haven't really shown that, but it's quite interesting to measure professional musician and student, because you can really see from their motion all the learning process. Professional musicians are extremely precise in their movement, and when you take a student, just the curve you measure is much noisier, and it's quite interesting to see. So, just to show you, then one of the applications of all this is by doing all this measurement, we end up building systems to measure acceleration on the bow, and that was, for example, used by a violin player, featured recently in the New York Times, Mari Kimura. And then you can see one of the examples where she's actually mixing the acoustic sound of the violin with some electronics. So based on our studies, we were able to make systems that were able to detect different type of motion, and the different type of motion trigger different sounds. So it just, you see, I mean, she's able to extend her vocabulary of adding new gesture to the regular violin gesture. So now, second part, talking about a tool that we've developed based on all these measurements, thinking, okay, now we measure all the musician, we can really think about the tool, how to analyze in real time the measurement, and we end up with what we call the gesture follower, which is a gesture recognition system. So what we found with this measurement is that a lot of information lies in the temporal evolution of the data. That we really want to track the gesture in time, to track the time progression, and then characterize different similarity between templates. Okay, I'm going to skip that. So the tool we developed, actually, it's much more general than gesture. It really works for any type of data stream that you can get from various type of motion capture system, either video-based or sensor-based, or even from sound processing. Now, for some people in the room that might enjoy the modeling is, that's quite standard to do in gesture recognition system, is to use hidden Markov models. So we use that, but we twisted the way normally people use the Markov chain. So the idea is that that's the motion, and to model that, you consider state, and every state can actually emit within some probability density function the value, and then you can progress over time with kind of random path through the states. So it's like a random walk. So getting quite close to a lot of things I've been doing before studying photon. So you can imagine different structure, different way to structure. And at the end, what we're able to do is that if you have one recorded example, and then you perform something, we're able to synchronize or try to understand how a new measurement find all the correspondence between what we measure and the templates. So we can do time warping and re-synchronize the two shapes. And once we've done that, we can actually compare. And for Jerry, I need to show that. What we actually do is we calculate the density probability function over all the states. And we can do that in simple case exactly, analytically, because it's most of the time it's a 1D problem, quite simple. But recently, for some cases that were more complex, we started to do particle filtering, which is actually type of Monte Carlo. And I must say that I haven't really, that's my student who really proposed to do that, and I thought it was a bad idea. Because for me, Monte Carlo was really not for real-time processing. But they show me that it's actually working quite fast in this type of application. So that's something we're actually working on. So I'm just going to show a short demo of the tool. So I'm going to record, just with the mouse, something. 1, 2, 3, 4, and I have recorded my voice at the same times. O, ah, O, 1, 2, 3, 4. So you see the systems recognize what I'm doing. One of the originality of the system is that it starts to recognize as soon as the gesture started. We don't wait to the end of the gesture. And then since the voice was initially recorded with the gesture, if I just redo it, it just playing the sound. I can change the spin speed. 2, 3, 4. Etc. So that's something. That's a tool that we then use in actual situation, and that's showing you with a string quartet that has been used for performance. When you see actually the systems align in real time the acceleration of the bow for every musician to a template. So what's interesting is that once you have realigned everything, you can really look at all the differences. For example, here, he played before than he used to play with the first recording. So you can really look at all the differences. So here's another very concrete application. It's exactly what I show with the mouse, but this time this guy controlled the recording of the orchestra with his motion, with a sensor attached to his wrist. So the orchestral sound, the speed of the sound is adapted to the speed of his gesture. So he's able to play with the piano, adapting the speed to the speed of the piano. So, I mean, the idea is just to create new situation where with this type of digital technologies, you can play music in a different way. It's not, the idea is not to replace the orchestra. It's just that to give new opportunities. It's another case, I need to accelerate a little bit, where you can see these are videos in the back of the dancer, and each time the dancer do a gesture, the system tries to display the video recording and synchronize the recording with what he does. So sometimes the system is lost. And now the dancer starts to play with the... So it's really playing with his own image. So that was also, I'm not going to show that, but that was used in actual dance performance in the context. And the same idea in installation. I'm just going to skip that to go faster. Just want to say that with these tools, when we end up really working with some dance companies on really working on the idea of pedagogy, education, these tools can actually help music education or help education in dance or in motion. And I think it's a very, very important type of application that could have a huge impact in the future. So MI, which is of course musical interfaces. Last part of my talk, which is the more fun, I think. Then we had all these systems to analyze and understand the motion. What was missing at some point is actually to really build object interfaces to use. So I coordinated a quite large project with 7 partners, academic and industry and designer, and then we really thought about this idea of to have something modular, a small interfaces you can use in many different ways using our software technologies. So that's actually what is displayed at MoMA right now. I'm going to show the video. So it's not MI, it's Mo. So it's a small interfaces with accelerometers and gyroscope inside, sending wirelessly all the data. And depending on the motion, you have different sound behavior. So here it's not trying to play notes, it's just to interact with sound. So motion is one thing. So no. So if you use it in a very energetic way, you can have a totally different sound environment. And now the idea is that you can add accessories to the small interfaces. So you can add piezo sensor, and then you can make an interactive table. So actually, this example was actually really used as to train rhythm and try to train to play together without the constraint of an instrument. You just have to exchange and throw the ball in rhythm to play the music. So that's the conducting example I've already shown. So either you conduct normally, but if you stop, you can freeze the sound and then suddenly work on modifying the sound. So here I'm going to redo. The speed of playing is really adapted to the speed of my motion. So this whole concept is actually shown as I said, in MoMA. And okay, we don't see that much. Just the idea is that really, with all the gesture recognition system we have and this modular object, we can really think about playing music totally in a totally different way, with the idea that you can replay something reusing something you know how to do it. Or you can have the idea of reusing existing object. So it's there are sensors in as before in all the different systems. Etc. And just one note, because what's interesting is that here we have, again, our piezo sensor. We are able to actually detect the type of scrubbing. So you can really attach a different sound to every scrub. And then it's really, it's like if you have different way of playing a drum, then you have different way to. Actually, there is a drum loop attached to every sponge. So we actually won a prize this spring with all this concept. And so going back to what you see on the right, as I said at the very beginning, why not using actually a ball? So what you hear is that there is a sensor, accelerometer, one of the small modules we made inside the ball. So we created actually games of very different type. So all the sounds you hear are really electronic sound that's added to the bowl. So it's quite interesting to suddenly transform this type of interaction with sound. So depending on how you play, you have different sounds. Oops. And now, especially the last thing for Bruce. So we end up doing actually installation just in front of the ircam, painting underground a special playground. And so for 10 days there were people coming and playing with kids and different way. And one of the game was a kind of a basketball. So all the sounds are really coming from moving the ball. So if the game accelerates, then the music accelerates as well. And depending of which team mark point, then the music change. Etc. So I hope that we can do a beach volley version in California. So being serious, I think that there is a huge potential also from a commercial point of view, because what I've been showing is that we are in a situation where we are actually between listening and performing music. And that's really bringing a new way of thinking about interacting with sound. Also, the type of game I've just shown, I think it's quite interesting because it's kind of video games without video, without screen, and you're in the. What's very interesting with this type of situation is that you have really to play together, to watch each other, and play collectively. And to go back to a more scientific project, I think now I'm kind of at the end of a phase with everything I've shown, and what's really interests me right now, and I'm going to start a new project. I got a grant to really study sensory motor learning. I mean, how do we actually learn to play and how to learn motion? And the fact to have sound systems is very interesting because you can use the sound as a feedback. So for example, for rehabilitation, you can use sound to guide your motion. And that's things that have been tried, but I think there are nothing really, there are still a lot. Well, there is one thing missing, is that a really good understanding and how the sound can actually enhance the gesture, the motion perception. And also for all this new idea of musical instrument, the learning process is very important. And that's where all the video games have been quite successful, is that it's kind of built-in video games that you can learn how to play it. So it's again this idea that digital technology can make instruments that easy to play, because I think it's impossible. What we have to do is to make instruments that easy to learn, and that's really something different. So it's not instantaneous gratification, but try to create an environment where we can actually progress in time. So there are many, many people involved in everything I've shown. We need to acknowledge them, and several projects. So that's it. If you have questions. So I hope I wasn't too long.
No, it was fantastic. And you got the book on it too, so it's very good.
Yeah. Fred, I have a question that we talked about before, but I don't know your latest answer to it.
Yeah.
It's very easy to make a quick decision.
Yeah.
What if you have four very similar ones like cursive O, cursive A, cursive C, cursive D? They all spend a lot of time doing the exact same thing.
Yeah.
What's your system for deciding when to make a decision about it?
Well, then it's a probabilistic decision, so it's going to be confused at the beginning. Of course, if they all start in the same way, the system will have a hard time to decide which one it is. So it's then within the design of your application, if you can, either you design the gesture you choose, you make them differently from the beginning because you want to have a very good answer from the beginning, or in the application you can deal with ambiguous beginning and really work. You don't have to take a decision because you have actually similarity measure probabilities. So it's okay if they are all at the same level at the beginning. You can imagine like a mixing board, and you can have a mix of all the sound at the beginning. And when you advance into gesture, then one sound is going to end up stronger at the end.
So it's really when one thing starts producing
Yeah,
something
yeah. Yes.
Is there any chance that you'll hook up an EEG to someone as long control music with their brain?
Well, yeah, that's a good question. Oh, okay. Yeah, I mean, people are doing that. I mean, some people are trying that. I mean, right now the problem is that you don't have a lot of control. I mean, you can, of course, distinguish if you really meditate or if you really make, or if you concentrate on something, then you can detect the difference. But it's quite poor, from my point of view, it's quite poor as a control mechanism. What actually interests me in the moment is really to think about more imaging systems to try to understand the learning